Welcome in here to our next video on Chapter 10, Nuclear Chemistry. In this video, we'll start to try to recognize when we have unstable nuclides. We'll build some intuition about why these nuclides are stable versus unstable, and we'll try to be able to predict what sorts of radioactive decay processes might be relevant for each type of nuclide. Lastly, we can use our new equations to quantify the energy stored in our nucleus. In our last video, we introduced different types of radioactivity, including alpha decay, beta decay, gamma decay, positron emission, and electron capture. And we said that these processes occur when we have an unstable nucleus trying to become more stable. In this video, we'll look at, well, why are some nuclei a little bit more stable than others? And can we predict when each of these processes might happen? We can start with a few rules of thumb for when our nuclei are stable. And we'll try to revisit this at the end as well. As it turns out, nuclear stability is based on really high-level chemistry and physics, which is outside the scope of what we get to do in our course. But we can look at some rules here to give us at least a little bit of intuition. What we can see is, well, statistically, there's not that many stable nuclei. And of the nuclei that are stable, most of them have an even number of protons, or an even number of neutrons, or an even number of both protons and neutrons. That means if we see a nuclei that has even numbers of protons and neutrons, it's more likely to be stable than one with odd numbers. Better than our even numbers are what are called magic numbers. These have special properties where it's almost analogous to our electron shells, where our noble gas electron configurations are more stable than other electron configurations. There are certain numbers of protons or neutrons that are more stable than others, which we call magic numbers. 2, 8, 20, 28, 52, 126, these are the first few magic numbers. And so having, well, 2 protons is very nice. Having 2 neutrons, also very nice. If we have 2 protons and 2 neutrons, this is called double magic. Something like helium-4 has exactly 2 and 2 protons and neutrons. Another example, oxygen-16, is also double magic. It has 8 protons, 8 neutrons. Cool. That turns out to be extra stable. Beyond these quick rules of thumb, we are going to have some mixture of protons and neutrons, and it ends up being, well, at least for our early elements, approximately a 1-to-1 ratio, equal-ish amounts of protons and neutrons. And then as our elements get heavier, we need to have extra neutrons to keep our nuclei from falling apart. To help us out, we can think about what's known as binding energy, the energy used to keep our nucleus together. And so let's peek at that now. Inside of our nucleus, we have our protons and our neutrons. When we have multiple protons in the same place, however, we need to overcome the repulsive forces of multiple positive charges living in the same spot. Like charges repel each other, which means our protons in the nucleus are all repelling each other, just like 2 magnets pointed at each other the wrong way repel each other away. To counteract this, there needs to be another force in the nucleus that is stronger than our electromagnetic forces. There is something in our nucleus keeping those protons bound together in the same spot, even though the positive charges suggest that they would repel each other. The answer to this is that there is what's known as the nuclear strong force, or perhaps the strong nuclear force. This is another elementary force of nature, along with gravity, along with electromagnetism, which works only on the scale of nuclei and is a force that is extremely strong on this small scale. It keeps our protons and neutrons bound together in the nucleus, but only works on that scale inside of the nucleus, distances about 10 to the negative 15th meters. What that means in practical terms is that inside of our nucleus, there's repulsion from our protons repelling each other, but there's now also this strong nuclear force keeping our protons and neutrons glued together. And for our stable atoms, that strong nuclear force is enough to keep it intact. For our radioactive nuclides, that nuclear strong force might not be enough to keep our nucleus together for a long period of time. We can highlight the importance of our neutrons here. Neutrons do supply some of this strong nuclear force. They can act as a glue that keeps our nucleus together. Since they add that strong nuclear force, but they do not add any extra positive charges, they're tipping the balance more towards staying intact and allows our nucleus to remain as, well, a nucleus. This ties back into what we were saying before. For our larger atoms with lots and lots of protons, we're going to need some extra neutrons to keep everything glued together. Those neutrons will provide our strong nuclear force to overcome our repulsive electromagnetic forces. We can look at this graphically. This is a chart of nuclear stability. On the y-axis, we're going to plot the number of protons in our nucleus. On the x-axis, we're going to plot the number of neutrons. Each pixel on this graph represents a very specific nucleus, a certain number of protons and neutrons. We can see some colorful squares and some empty spot above and below these colorful boxes. The colorful boxes represent atoms that can exist for at least some period of time. The greens and the blues and the yellows, and some of these little pink boxes out here, are going to represent our radioactive nuclides. Meanwhile, the black pixels, the black squares on this chart, represent our stable nuclides. We can notice there's only a handful of these black pixels. There's only a handful of stable nuclides. Most of the possible combinations that might show up in the world are going to be radioactive. Moreover, we can see that early on in our chart, when we have only a few protons and only a few neutrons, well, this ratio is close to 1 to 1. If you zoom in, you can look at our black pixel for helium corresponds to 2 protons, 2 neutrons. For oxygen, it corresponds to 8 protons, 8 neutrons, and so on. We can have this 1 to 1 ratio, at least early on in the periodic table. As our atomic number increases, however, we're going to need extra neutrons in order to remain stable. We can try to visualize this kind of 1 to 1 ratio of protons to neutrons as this red line. Early on, our black stable squares correspond to, approximately this 1 to 1 ratio. But later on, in order to remain stable, we do have to have extra neutrons. We do need to have these neutrons supply that strong nuclear force and act as the glue that keeps our nuclei together. If we like, we can refer to this strip of black stable squares as our valley of stability. These are the only nuclei that will last indefinitely. All the other ones will undergo one type of radioactive decay or another until they can get closer to that valley of stability and land on one of those black squares. We can use this chart to give us intuition about when we expect different types of radioactivity to occur. If we're thinking about alpha decay is when we emit an alpha particle, 2 protons and 2 neutrons being lost as we form our daughter nuclide. Losing a helium nucleus means that we're going to lose 2 protons. We're going to move down on this y-axis 2 squares. Losing that helium nucleus also entails losing 2 neutrons, we're going to move to the left on the x-axis exactly 2 squares as well. The net result, ultimately this is moving diagonal and to the left at this 1-to-1 ratio for our alpha decay. We can think about when this process will get us significantly closer to our black stable nuclides. And it's going to happen when our nucleus is originally above that valley of stability and significantly out here at the top right of our valley of stability. When that's the case, moving down and to the left diagonally here does get us closer to our stable nuclei. We think about it the opposite way. If we're underneath our valley of stability and we go down and to the left, this actually gets us maybe a little bit farther away from those stable nuclei and is not going to be helpful. The conclusion that we can draw here, alpha decay happens when we are above the valley of stability, when we have our protons versus neutrons graph. And as it turns out, happens when we have very large nuclei to begin with as well. This is highlighted in these yellow squares up here. These yellow squares are elements that go through alpha decay. For beta decay involves a neutron turning into a proton and an electron. When we undergo beta decay, we lose a neutron and we gain a proton. Here is that beta decay process. When we lose a neutron, we have to move left on our neutron axis. When we gain a proton, we have to move up on our proton axis. Overall, this process will allow us to go up and to the left on this chart of nuclear stability. That means our nuclei that will undergo beta decay are ones where we can get closer to our stable nuclei going up and to the left. That means we need to start underneath our valley of stability. And when we undergo beta decay, we will get closer to our stable situation. So again, our conclusion here, beta decay is going to be the process that occurs when we are underneath our valley of stability on this protons versus neutrons stability chart. We can see those highlighted in teal on this graph. Everything under those black squares is color-coded as beta decay. We can think about positron emission next. This is when a proton turns into a neutron. And so we are going to be losing a proton and gaining a neutron. So in total, we're going to be moving down and to the right on our stability chart here. We can see this color-coded in green. We're going to have positron emission as a possibility when we are above these black stable nuclei, trying to get closer by moving down and to the right. Positron emission is going to be more common for our smaller elements, whereas we had alpha decay for our much, much heavier elements. Lastly, we can consider our electron capture process. This is when we have a proton combine with an electron to produce a neutron in our nucleus. We are going to be losing a proton. We are going to be gaining a neutron. And so again, we're going to be moving down and to the right on our stability chart here, protons versus neutrons. What that means is our electron capture process will be possible for most of our elements that could also be undergoing positron emission. Again, these elements are color-coded in green. For us, we won't need to worry about when we expect positron emission as opposed to electron capture. In real life, there might be some mixture of both of these processes happening with different probabilities for each process happening. We can zoom in on this chart for a second and visualize some of these processes. Here is the decay series for uranium-238. Uranium-238 is this square highlighted in red at the very top right, and is a nuclide which is able to undergo alpha decay. We lose 2 protons, which means we go down 2 squares. We lose 2 neutrons, which means we go left 2 squares, and we end up with thorium-234. Thorium-234 is unstable, but in the opposite way. It needs to get its ratio of protons to neutrons a little bit higher, and so it undergoes beta decay, moving up 1 square and to the left 1 square as we have a neutron turn into a proton. We end up with Pa34, which also undergoes beta decay. Now we have uranium-234, which is unstable and will undergo alpha decay. We end up with thorium-230, which also undergoes alpha decay. Radium-226 also undergoes alpha decay. Radon-222 also undergoes alpha decay. Polonium-218 also undergoes alpha decay. Now we have lead-214, which is unstable in the opposite direction, undergo beta decay. Bismuth-214 also beta decay. Polonium-214 is going to undergo alpha decay. Lead-210 is going to undergo beta decay. Bismuth-210 beta decay. Polonium-210 alpha decay. And finally, we've landed on one of these black squares. We've ended up at a stable nuclide, lead-206. For any of these processes, I'd expect us to be able to write the nice balanced reaction if we knew which type of radioactive decay to expect. And we should know, generally, that these decays will keep going until we land on one of our stable nuclides. This decay series for uranium-238, it is characteristic of this specific nuclide, uranium-238. And so we can look for evidence of this series of reactions to prove that our uranium-238 might be present. We could have other decay series for other nuclides, and this is actually good evidence to prove that maybe we've synthesized a new element if it produces the series of alpha and beta decays that we'd expect from some of these new synthesized massive elements. We can summarize here again. These are the radioactive decay processes we've talked about. When we are below the valley of stability, beta decay is the only option. When we are above that valley of stability, well, we have a few different options. Alpha decay for our very, very massive elements, and then positron emission, electron capture as possibilities for most of our lighter elements. The last thing we can do here in this video is to try to quantify the energy that's being used to keep our nuclei together. This is known as the nuclear binding energy. There is some energy being used to pack all these protons and neutrons together in that same place. This is the nuclear strong force, but we can quantify it using our famous Einstein equation. What we know is that mass has to be conserved, at least under most circumstances. There's an exception here, and it's the fact that, well, matter can be converted into energy. Here we can see this illustrated when you build a helium atom. If you're starting with 2 protons and 2 neutrons and 2 electrons, we can add up the mass of our protons, neutrons, and electrons. We end up with this number, 4.0331 AMUs, for the mass of our helium. In reality, however, every helium that you find with 2 protons, 2 neutrons, 2 electrons actually only weighs 4.0026 AMUs. This is lighter by just a little bit, but it is lighter. We've lost some mass. Well, that mass hasn't just disappeared. We haven't destroyed that mass. That mass has been converted into the energy that's used to keep our protons and neutrons packed together into that nucleus. This is known as the mass defect, and we can say that our mass defect is caused when our mass is converted into energy. We have an equation for mass and energy equivalency. It's this famous equation from Albert Einstein, E is equal to m times c squared. The energy that is keeping our nucleus bound together is equal to the mass that we've lost times the speed of light squared. In order for this equation to work out, our energy is in units of joules, our mass is in units of kilograms, and the speed of light is in units of meters per second. If we want, we can convert after the fact. Oftentimes, this is reported in units of electron volts, or perhaps mega electron volts. We add that metric system prefix. Here's our conversion. 1 electron volt is the same thing as 1.602 times 10 to the negative 19th joules. Let's do an example problem together. Can we calculate the binding energy in our fluorine-19 nuclide, which has a known atomic mass of 18.998 or AMUs in all these different units? We can start by calculating our mass defect. The mass of our fluorine nucleus is going to be 9 of these protons and 10 of these neutrons. We expect our nucleus to weigh 19.1527 AMUs, but it only weighs 18.9984 AMUs. The difference in mass here is how much mass has been converted into energy. The difference in mass is going to be the m in our equation. We can plug this into our equation. Again, be careful with units. We don't want AMUs. We would rather have kilograms, and then we'll use the speed of light squared. Here's our mass. Here's our speed of light squared. The energy in our fluorine nucleus is 2.307 times 10 to the negative 11th joules. For question A, we're looking at joules per mole instead of just joules. So we need to multiply this by Avogadro's number to get joules for every mole. Here's our answer for question A. We have 1.389 times 10 to the 13th joules per mole. This is a ton of energy. If we remember our unit on thermodynamics, hundreds of kilojoules or maybe thousands of kilojoules per mole is what we might expect for the energy from certain combustion reactions. This is orders and orders of magnitude more than that, just stored in our nucleus. This massive amount of energy is what makes things like nuclear power so enticing. There is a lot of energy in there. The question just is, how can we harness that? For question B, we can do a slightly different conversion to find the MeV per nucleus for our fluorine atom. For question B, we can take our answer from before and convert from joules to electron volts, and then use the metric system to go from electron volts to mega electron volts. 1 mega electron volt contains 10 to the 6 regular electron volts. We end up with this value, 144.0 MeV per nucleus. You can see why units of mega electron volts might be convenient here. Certain nuclei have different amounts of energy stored within them, but they are on this scale of mega electron volts. All right, there we go. As promised, we can revisit our intuition here. Even numbers of protons and neutrons helps us out. Magic numbers helps us out as well. And the binding energy in our nucleus per nucleon is also going to be important. Does adding or removing some of these nucleons, protons or neutrons, does adding or removing some of this change the amount of binding energy we might have? We can quantify that binding energy now using our E equals mc squared equation. And if we have access to our chart of nuclear stabilities, which is available linked below on this nice handy website, we can find out whether any particular nucleus might be stable. We can also try to predict what kind of radioactive decay might occur. that'll be it for this video. Thanks for hanging in there. Please let me know if you have any questions, and we'll see you all soon. Thanks so much.